Hello everybody. Let's start data visualization lesson 3. Okay, as usual we just import the NumPy as NP and we import pandas as PD and matplotlib.pyplot as PLT. And with that being said, we can also import OS. So I said that the directory that I have, I change it to my directory that I would like to have. And so in this lesson, in this chapter, we are going to be covering some of the most commonly used plot types, such as scatter plots, bar plots, box plots, heat map plots, and many others, pie charts. But we'll also be utilizing some more rarely used plot types. So we'll be studying bar plots, pie charts, scatter plots, bubble plots, histogram plots, box plots, volume plots, stack plots, heat maps, and 3D plots. And in addition to that, all of that, we are going to work on creating some custom plots, some like a joint plot, which isn't built into Matplotlib library, but it's popularized plot type of Seaborn, which is very famous. Okay, let's get started. We are gonna start with line plot, which we have had before, but let's just work on them a little bit more specifically. Line plots display numerical values on one axis and categorical values on another. They can typically be used in much the same way that bar plots can be used, though they are more commonly used to keep track of changes over time. Okay, so that's a definition of a bar plot, and then we are going to have a few examples and we'll see what's going on. And I changed my directory. I'm going to cut this here. And then this I'm going to have a data set called df1. It's GDP per capita of different countries adjusted for purchasing power parity. So if you want to compare different countries, you got to use this data set. And then let's see what's going on here. Here we have GDP of, I think, up to 240 countries for years. So right now we have country name, we have and years from 1990 to 2020. Okay, and then I'm gonna just play with this dataset a little bit. First, use the T attribute to transpose method or to swap the rows and columns or transpose our dataset. So it's gonna be df2 equals df1 dot transpose. Instead, I could just say df2 equals df1 dot t, but remember here for transpose, it's a method, so I need parentheses, but for just use t because t is attribute, I don't need a parentheses. Okay, now let's take a look at df2 info. As we see, we have 32 entries and we have 266. So the first row that we after transpose, when we transpose the data, the very first rows is indices that we don't need them. However, and then here we have country name. Maybe we want to change this to year, and then we have different countries. So what I want to do is that columns name, I want to be, let's set the first row as a column names. Yes. So df2 columns is going to be df2 dot ilog 0. So this is row first, row index 0. Yes. This is row index 0. If I do this, and then I'm gonna have I have changed my df columns. If I take a look at df2 head, now it's gonna be something like this. So I don't need this, the first row or row index 0. So I want to delete that because of that. So to delete row index 0 first row, I do this. I say df2 equals df2 dot ilog 1 and anything after that. So if I do this and then I run df head one more time, df2, I just call this data set df2. Then you can see what's going on. Yep. Then in addition to that, maybe I want to change a reset index. Let's see the index as a column. This one is an index. I don't want it. I want it to be a column. So if I do that and I run the F2 head, this is going to be the result. Country name now is like the index is from 0. And then we have a new column called index, and it's from 1990 to 2000. So I want to change the name of that column from index to year. So I use df2.rename and then columns, the old name, then column, new name. So I get this one. Now I have year is my first column, and then each country is like another column. Okay, with that being said, let's plot world, United States, and United Kingdom. So I have 3 countries. I want to draw them. So I said I'll say fig comma x equals PLT subplots fig size 9 and 7, and then I plot df2 column year, so in brackets quotation mark year, and then df2 column world, and I label it as world, and I want it in color blue, and then I do the same with United States. I label it United States, and the color would be red. And then year, df2 year versus df2 United Kingdom. The label is going to be United Kingdom. Let me run this and see. So this is the result. I have 3 labels: world, United States, United Kingdom. I want United Kingdom to be in black, world to be in blue, and United States to be in red. And it's their GDP per capita. And then I want my y column to be between 0 to 70,000, and I want my X text to be rotated 90 degree, and I need a legend, and I let Python to choose the place for my legend. So with that being said, I run everything and I get this result. Okay, now consider, for example, X is linear space between 0 to 8. So it's linearly divided to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points. So it starts from 0 and it ends at by 8. And the whole number of points is 10. With that being said, and I want my y to be just exponential of x. And if I plot this, as you can see, it's very exponential. So we always have the option to use logarithmic scale. If we do that, it's going to be plt.y scale, and then plt.y scale in parentheses dot log, in parentheses quotation mark log. So if you do that, now look at the y ticks. It's going to be 10, 10 to power 1, 10 to power 2, 10 to power 3. So my y scale is logarithmic. Therefore, it's going to be a straight line. So you can choose your y scale to be logarithmic or not. Okay, that's it about the very first section that we had. And we started with line plot and then we moved to bar plots. So we started with line plots. Second plots that we are going to talk about is bar plots. Bar plots display numerical quantities on one axis, typically vertical, and categorical variables on the another one, which is usually horizontal, letting you see how many occurrences there are for different categories. On the other hand, you don't have to plot the number of occurrences. You can use any estimator function to aggregate the data. Bar charts can be used for visualization in a time series as well as just categorical data. Okay, how do we do that? Calling the bar function on the pyplot or axis instances and passing in categorical or numerical variables that we would like to visualize. So let's work with the data set that we had in previous chapters. A part of that data set, very simple one. What's the data set? Just four names: Surush, Jamie, Kiana, Arash, and then height is in inches: 74, 65, 60, 75. And then with that being said, I want to plot the name versus height of each person. Very easily done. You can do it like this. And of course, you can easily do the same thing with with X. So if I want to do that with X, that's going to be something like this. So I just add this line fig comma x plt subplots, and then I pass in the size I want. And then with that being said, just rather than plt.bar, I'm going to have x.bar. And then that's it, just plt.show. And as always, and you get this with x. So this is equivalent to this. So or equivalently, you can do that. That's example number one. Example number two, let's say I want to draw year versus United States, and there's going to be a label. So I'm going to run this, and then let's see, I'm going to explain what's going on. So this is GDP per capita of the United States. And as you can see, generally speaking, it goes up. Every now and then it goes down. For example, 2009 it went down, and then 2020, whenever we have a crisis, it goes down. 1991 it went down from 1990, but generally speaking, the trend is upward sloping. And then, so what do we have? As always, we start with fig comma x plt.subplots, and then here I have x.bar df2 year df2 United States. Label is United States and color is red. And then I have y limit from 0 to 770,000, and I want my x ticks to be rotated 90 degree, and then I want my legend to be there as well, and with that I get this curve. Example 3, having a horizontal line. So let me run this one, and then let's see the differences that we have. So here we are adding a horizontal line. So first three lines are exactly as before. Then we define the word mean as, or I can call it, I don't know, mean US, whatever I want. Yes, it doesn't have to be. Mean US is df2 United States dot mean, and then here I say x dot x h line mean underscore US, and 0 and 1 and color equals C. Which is cyan, and then label is mean value for data sets, and then everything else is the same again. So the only thing that they added is this line x.xh line mean US. That's the only difference, and I run that and I get this result. Okay, example number 4, plotting two charts. So here I'm plotting year versus United States and year versus United Kingdom, and I want my legend to be upper left. Very easy. So when you do that, however, just notice that they are on the top of each other. So that the red part is the difference between United States and United Kingdom. And but the color for the United Kingdom is yellow. Okay, example 5, plotting means. Now I have, let me run this one. So here I have, I'm comparing the mean GDP of the United States with United Kingdom with world. So X bar is going to be DF2 year, DF2 United States. Sorry, here. X bar is going to be US. So on the horizontal, we are going to have this US and then df2 United States mean and label United States and then red. So here we are giving Python the xticks that we want Python to use. So it's going to be US and then df2 United States and then x bar UK df2 United Kingdom dot mean and then x dot bar world the df2 world dot mean and label. So here is a problem. I have to fix this label here. I want it to be world because I copy and paste. I forgot to fix it, and I want my chart to be from 0 to, yeah, but here it works. It works very well, and you can compare the mean of GDP between these three countries. Example 6, plotting horizontal bar plots. So let me run this code and see what's happening. So here we are not going to use x.set y-lim from 0 to 70,000, or we are not going to rotate xticks 90 degree. I'm going to get rid of them, but everything else is going to be the same. The only difference is that we are going to say x.bar h. For all of these categories, we are going to use x.bar h. And then we're going to have the legend. Now, sometimes you want to also add a text. Yes, you can add any text that you want. But let's say that you have something A, B, C, D, and then run this. Very simple chart, A, B, C, D, and then Y is 1, 2, 3, 4, and I want to add a text. How do I do that? I can do that like manually. How? I can just say for index and value in enumerate Y, x.text, index value, and string value. So what's going on? So here, enumerate Y is like numbers 1 to 4, yes? And then these numbers will be added 1, 2, 3, 4 will be added to our chart. So we are giving the coordination that these numbers want to be written. So index and value, and then after that, what we want to be printed, we want to be like these numbers 1, 2, 3, 4 to be printed there. Another example of adding text. This is maybe if you didn't understand that one, this one is better. So I'm going to run it first and then explain what's going on. Now, look at this, what's happening. Let's see. So I'm saying X is a list. So first of all, I have fig, comma X, PLT subplot, fixed size line 7, as always. Then I'm defining two lists, list X, list Y. List X is 3 words, US, UK, world. Now, what's list Y? It's, so forget about the round. Here I have df2 United States, that means, so that's the mean of the United States GDP. And then I'm rounding that up to 1 decimal. And I do the same for the United Kingdom, and I do the same for the world. So I get these three numbers. So y right now is a list of three numbers: 51699.9, and then 39575.5, and then 12682.3. So y is a list of three numbers, and then I say x dot bar x and y, and then I say for index and value in enumerate y, x dot x index minus 0.1, value plus 1,000, and string value, color 1 to be red. So I'm printing these numbers in red. Now the first two, I'm giving the coordination of my text. Yes. So if I don't give this plus 1,000, what's gonna happen is that it's gonna the text is gonna be like exactly over like somehow I don't have this cool space anymore. I don't want this. I want to have a space there, right there. So what I do is that I say rather than value plus 1,000. Okay, when I do this, as you can see, now they are not exactly, they're a little bit up compared with the one that we had before. Here it was over the shape, like touching the shape. Now they are not touching the shape. They're a little bit above the shape. And then, yeah. Okay, that's it for, so just remember that this index gives us, index minus 0.1 gives us the x coordination, and then value plus 1,000 gives us the y coordination. Okay, that's it for second type of charts, bar plots. After bar plots, we want to talk about pie charts. So next chart that we want to learn is pie chart. Pie charts represent data broken down into categories or labels. They are an intuitive and simple way to visualize proportional data such as percentages. So we usually use them for percentages, something like that. The main difference is that pie charts are mainly used with proportional data where the sum of all the categories add up to 100% or number one or 1 unit, instead of plotting the number of instances or aggregations of data like bar plots. To plot a pie chart in Matplotlib, we can call the pie function of the pie plot or access instance. The only mandatory argument is the data that we would like to plot, such as a feature from a dataset. Let's have one example. This example is a real example of the percentage of what percentage of Americans are white, Hispanic, black, Asian, Indian, and other races. So this data is from Wikipedia. 51.6% of Americans are white, non-Hispanic white. 23.1% of Americans are Hispanic, either white Hispanic or black Hispanic or whatever. Then black is 14.6, Asian is 6.4, Indian is 0.8, and all other races are 3.5%. That's a data set. I'm going to run that. So we have, oops, So because I resetted my computer, I have to run this codes first. And now I get back to my data sets. Okay, this is the American demographic. Now we want to make this data set, convert this data set to a pie chart. First I'm going to run this and then explain what's going on. So this is a very basic step. You can see that there's a circle, and one of them is like the blue and the orange and then the green, red, purple, brown. It's not very obvious what's going on there, what is what. Because of that, let's add some characteristics to this pie chart that we just had. So this doesn't give us that much information. I'm going to run this code. This is way better. It has a title. The title is US demographic. And as you can see it here, it's like 52% and stuff. So a couple of points is, first of all, is that still the size is small. The reason for that is that I said 9 and 7. 9 and 7, and let me try, for example, 8 and 8. When I do 8 and 8, as you can see, it's bigger. So because output is going to be no matter what square of information, so 8 and the Python is going to take the smaller number. So 8 and 8 is going to be better than 9 and 7, or even better than 9 and 7. I'll do 9 and 9. Yeah, you do 9 and 9 and it's even bigger. And so we have fig ax plt dot subplots fixed size 9 and 9. Color list, we have a color list: blue, orange, gray, green, red, cyan. And then we have axpy df percentages, and then we have labels as well. What are the labels? Labels are df categories. So all those categories that we have are going to be labels, and then colors would be equal to color list. So color list is just a list. And here with this auto pct percentage sign 0.0, I'm saying that I want no decimals. I could do this. Yes. If I do this, then it's going to be like up to 1 decimal. And then we have a set title, US demographic, and then plt.show. So to add numerical percentages to each slice, we use the auto pct argument. It automatically set the percentages in each wedge or slice by setting auto pct to 0.0, let's say 1.1 f. We have chosen to format the percentages with 1 decimal places, and added the percentage sign at the end. If we had omitted the surrounding percentage sign, the string wouldn't be formatted as percentage, but as literal values. And so if you want to use another computer, this like when I was typing these codes, at some point I used my office computer, which has a different path. All you have to do is to just do this os dot change directory, chdir, and change directory, and still you don't have to change like the codes, the actual codes here. That's the beauty of changing the directory. So the next type of plots that we will be working on is scatter plots. Scatter plots visualize the relationship between two numerical features. These variables can be dependent or independent of each other. So this data set scores edited. We have been working with this data set a little bit. It has this data of people, but it's generally speaking, it's their name, their gender, assignments, it's out of 200, exam 1 out of 150, exam 2 out of 150, exam 3 out of 150, final exam out of 350, I guess, and then the total, which is just out of 1000, and the alphabetical grade is I think like 30 students or something. So you can always check that with df info, how many, the characteristics of the data set. So we have 28 observations, 12 of them is object, 3 name, gender, and grade is objects, everything else is float. Now we are going to work with this dataset a lot. So, but just remember exam 1, exam 2, exam 3 are midterm 1, midterm 2, midterm 3. They're all out of 150. Now let's say I want the scatter plot of exam 1 versus final exam 1 on the horizontal axis and the final exam on the vertical axis. How do I do that? Just I'm going to run the code first and then describe it. But this is the code, and then the way it works is that first you start with fig comma x plt subplots, and you say the figure size. So again, it's going to be 9 inches by 6 inches. Then you say just x.scatter, and you determine your x and your y. So our x is going to be exam 1 of this data set, and then y is going to be the final column of this data set, and that's it. Everything else is optional, like plt.x label. So if you want to have an x label, you can, you don't have to. But as before, you can have like plt.y label, or rather than this, you could have like x dot set x label and x dot set y label. So you don't have to do that. But okay. Okay, so we have also set the x and y labels to indicate what the variables represent. There is a clear positive correlation, as you can see here, between exam 1 and final, between these two variables. The higher exam 1 score, the higher final exam score is. There are a few outliers, but the vast majority follows this hypothesis. So one outlier is right here. Exam 1 is a little bit short of 80, and then final exam another one here with the final exam a little bit short of 300, but the rest of them are right here. So that's when we want to have one plot. It's also possible to have two plots. Let me run this code and then explain. So here we have fig comma x plt subplot 2 fig size 9 and 8. So we have x index 0 and x index 1. X index 0 is Like before, df exam 1 versus final, x label exam 1, a y label final. We also have exam 2 versus final. However, here we are using the marker as unders. The marker is not going to be like a circle, it's going to be underscore. So that's different. You can always like mention and determine the marker that you want to use. And then again, here we have X label exam 2, Y label again final, and PLT show. So we have created two axes through subplots 2 and saved them in a single array of axis instances, accessing them through x0 and x1. Then we have called scatter on each of them, producing a figure with two plots. Nice. Customizing scatter plots in Matplotlib. How can we customize this? Okay, let's see. For example, here we are customizing a little bit. I have only one plot, exam 1 versus final, but the main difference is happening right here in x.scatter. So let's study that a little bit more carefully. So again, x is df exam 1 and y is df final, but here we are saying we want the color to be red, we want edge color. So maybe I can make it a little bit bigger, 10 and maybe 8 rather than 6, so it's more obvious. Edge colors, I want them to be black. Yeah, as you can see, they are inside the red, but there's an edge color, and the edge color, as you can see, is in black. And line width is 1, and alpha was transparency is 0.7. Another exam, so I'm defining a dictionary, M red, F blue, and then, okay, let me run this code and then explain it. Okay, I forgot to run color, and then I'm gonna just run this one. As you can see here, for gender, we have two genders. Now I want my male students to be in red and my female students to be in blue. Yes. So first line is as always, fig comma x, PLT subplot fig size 9 and 6, x scatter df exam 1 df final. Here's the difference. I'm going to say color rather than red. Now I have df gender dot apply lambda x colors x. So this colors is this dictionary that I have here. So I said x colors x, and I applied that to df gender, and then you'll get different colors for different um, genders. Okay, that's about scatter plot. Next topic that we have is bubble plots. Bubble plots are called so because they resemble a swarm of bubbles. They're typically each differently sized and transparent to a degree. Okay, with that being said, let's run this code and see how it works exactly. As you can see, for example, you have uh, it's very similar to scatter plot, but we have arc scatter. So as you can see, there are some circles bigger and some circles smaller. Yes. So you have df exam 1 is horizontal axis, df final vertical axis, but we have also s equals df exam 2. I can make it a little bit like more vivid. I can make it maybe bigger first of all. That might help us a little bit. But also I can, for example, here you can see this circle is really small, but this circle is bigger. But if I want them to be even more obvious, I can do this. I mean, it's really too much. I don't want Okay, yeah, this one is a little bit more obvious. As you can see, the size of bubbles are different, and then they are because the size of bubbles are different, we call them bubble plots. So if you want to make this size difference even more obvious, you can multiply that by 3, and then it's going to be even more obvious that the sizes are different in some of them. But the size of each circle is based on exam 2. Okay, next very important plot that we have is histogram plots. Plots are a great way to visualize distributions of data. In a histogram, each bar represents input data placed into ranges, which oftentimes they're called bins or buckets. Taller bars show that more data falls in the range in percentage or count. Histograms are very common in data science as a way to display distribution of the data. So let's see one very simple example. For example, PLT hist df exam 1 and PLT show, or equivalently you can do that with X, then you can make it bigger. By default, the generated histogram will contain the count or frequency of occurrences. So what's the frequency that we have? And it's this much. Another example. So changing a histogram's bin size. We can change the bin sizes. For example, here we will have bin equals 15, and as you can see, they are a little bit different. So here this one goes down after this, so we have more bins in the second one than this one. Yes, so you can do that. Or another example, so bins equals a number, tells you the number of bins that you want to have. You can also have bins equals, for example, np range, minimum of df exam 1 and maximum of df exam 1, and then 5 is step. So we have start, stop, step. So yeah, with that you get so first of all, np range, minimum of df exam 1 to max and df5 gives us 54.44, and it goes up by 5 until 144.44, but it covers those. Plotting a histogram with density data. So if we want the data to have the density data, we just say density equals true. And sometimes instead of the count of features, we would want to check what the density of each bar or bin is. So we don't want the count of each for each bin. We want density. When plotting with density data, all bins should sum up to 1 or 100%. So we can take a look at this example. So what's going on here? We are having we are having x and y. So what is each of these? So x is a random number, integers between 0 and 10, 0 inclusive, 10 non-inclusive. uh, 10 numbers randomly selected between 0 and 10. Y is 100 numbers randomly selected between 0 and 10, 0 inclusive, 10 exclusive. But then we wanna just we want to just show them here on our histogram. So what's happening? We are having two histograms on the top of each other. We say x.hist x alpha equals 0.6, so transparency 0.6, density equals true. So with that density equals true, we say we don't want the occurrences, we want the density. Label equals x, color equals blue, and then the other one, density equals true, label y, color red. And I want my legend to be printed to on upper left, and you run this code, you get this result. So another thing that you can always do is customizing the histogram plots. You can say, for example, fig x plot subplots and fixed size 9 and 6, df exam 1. So here we have bins equals 10, the number of bins. His type equals step. So you can get like select different histogram size. And you can pick the alpha. You can say align. So it can be right, it can be different things. And then orientation can be horizontal. That default is vertical. So I'm going to run this so you see that. So the histogram type is step, and then it horizontal rather than vertical. And log equals false, you can convert that true to true. So each of these bins is the number of bins in the plot. Density shows whether pyplot uses count or density to populate the plots. His type, the type of histogram plot, the default is bar, but though other values such as step or step field are available. Alpha is transparency of the lines and bars aligned to which side of the bins are the bars aligned. Default is mid. Orientation can be either horizontal or vertical orientation. Default is vertical. And log whether the plot should be put on a logarithmic scale or not. Okay, that's it about histograms. Next topic that we have is about box plots. Next chart that we want to talk about is box plots. Box plots are used to visualize summary statistics of a dataset, displaying attributes of distribution like data's range and distribution. Let's have an example. For example, this is the box plot for exam 1. We can adjust the size, make it a little bit bigger maybe, and here we go. So, and before going to second example, let's see what's going on here, and then we can have the second example. So box plots are used to visualize summary of the data through quartiles. A quartile represents a step at 25% of a dataset. So if we divide the dataset into quartiles, they are divided into Q1, Q2, Q3. Q1 shows is a number that 25% of data is less than that, and then 75% of data is greater than that. Q2 is the number that 50% of data is greater than that and 50% is less than that. It's also called median. Q3 is the third quartile, which means that 75% of data is less than Q3, and then 25% of data is greater than that. So whatever you have, for example, Q1, it means 1/4 of data is less than this. Q2 is 2/4 of data is less than this number. Q3 means 3/4 of data is less than this. So Q2 is effectively the median of a data set, while Q1 is the middle point, middle value between Q2 or median and the minimum value. So between minimum and median, there is Q1 is the middle point. Q3 is the middle value between Q2 or median and the maximum value. The quartiles at 0% and 100% are simply called the minimum and maximum. So 0% or Q0 means 0% of so Q0 is 0%, 100% are the minimum maximum value of a data set. The range between Q1 and Q3 is known as interquantile range. Yeah. So you can imagine Q0 means that 0% of data is less than that, which means minimal. Or Q4 means 4/4 of data or 100% of data is less than that. So it simply means maximum. Box plots get their name from taking the shape of a box. As you can see here, there's a box here, and with the distribution data within the boxes, there is a orange line. This orange line shows the median. The boxes are bound from Q1 to Q3. So here you can see Q1 is right here and Q3 is right here. So the box is between Q1 and Q3. Essentially, the boxes are interquantile range. Then in addition to box, we have whiskers. Whiskers are these lines right here and then right here on the top of the box and on the bottom of the box. Whiskers lines extending from the boxes let us know the minimum and maximum of the dataset after eliminating outliers. So you put the outliers aside. These whiskers show the minimum and maximum after eliminating those outliers. What is an outlier? Outliers are detected using IQR method. So IQR, as we just saw, is Q3 minus Q1, and lower outliers are those numbers. Lower outliers are less than Q1 minus 1.5 times interquantile range, and upper outliers are so lower outliers are numbers in the data that are less than Q1 minus 1.5 times IQR, and upper outliers are numbers in the dataset that are greater than Q3 plus 1.5 of IQR. So outliers are very easy to spot with a box plot as they are isolated outside the boxes themselves and extended beyond the whiskers. So these dots here, we have two lower outliers. Box plots are really the most useful for comparison purposes since they put things in the same perspective. You'll usually plot more than one box plot of several features to compare their summaries, for example, outliers, interquartile range, and etc. So now that we know everything about box plots, let's have the second example. So maybe I move the second example here. As you can see, we are having the box plot for exam 1, exam 2, and exam 3. In exam 1, we have 2 outliers. Exam 3, we have 3. Exam 2, we have 3 outliers. And exam 3, we have only 1 outlier. And you can see the median in the exam 3 is the highest. Median is in exam 2 is the lowest. Median in exam 1 is the F. Between those two, between all other medians. And you can see that the whiskers and everything that you want here. Okay, with that being said, you can plot the second example like this too. So either we can plot it like that or we can plot it like this. So what's the difference? Here we have them in different plots. Before we have them all in the same plot. Yes. This one we have them in different plots. This is especially better if your columns have different ranges. So if, for example, you are comparing exam 1, which is between 0 and 150, with final, which is between 0 and 350, and total, which is between 0 and thousands, then if you have them in different box plots, it's way more useful. So here you can see like the ranges are like totally different. For exam 1 is 60 to 140, the exam final between 100 to 350, and then total is between 400 to 900. Okay, customizing box plots. We want to customize our box plots. How can we do that? So here we have one example. We have so under horizontal we have x ticks. So far we added this x ticks 1 and 2 and 3. It's going to be exam 1, exam 2, exam 3. Rotation 90. We want them to be like vertical. That's one thing we can do. We can also do this, another example. So here I have to change this to x1 and then x2. But having that, if I run this, you see that we get, for example, exam 1, final, and total. So for each of them. Okay. Now, and remember that if you want to see the median of everything, you can get the median with this, and you can make sure that everything is correct. With dot median, you can find the medians. Okay, plot the box plot horizontally. So for all box plots that we graphed them, they were vertically. How if I want to do that horizontally? Like this, it's super easy. All I have to do is to add this term that vert equals 0. With vert equals 0, I can do that. Vert controls whether or not the plot is rendered vertically, and it is set to 1 by default. Another example that we have, some other variables here like notch and patch underscore artist. Let me run this and then explain what's going on. So here, as you can see, the notch equals true attribute creates the notch format to the box plot, and patch underscore artist true fills the box plot with colors. Then you can have a mean line. It's very hard to see here, the mean line, but it's the green line here. Maybe if I make this false and then run it. Yeah, now it's mean line is better. Mean line is the one in green. So you can always make this patch underscore artist either true or false, and then mean line equals true, and then when you have that, you want show means equals true as well. Okay, that's about box plots. Now remember that you can always mix and match between plots too. You can also mix and match between plots. Let's have an example and then we explain what's going on. So here we have 6 plots. One of them is empty, but I start with fig, comma, x, plt subplots, n rows 3, n columns 2, and fig sizes 11 and 6. So I want 3 rows and I want 1 column, 2 columns, and I want my figure size to be 11 and 6. And now I can focus on, for example, row index 0, column index 0. I want the first one, which is row index 0, column index 0, to be a histogram of exam 1. And I got a histogram of exam 1. Then I want my row index 1 and column index 0. So right below that, yeah. So left and center. I want that to be a box plot of exam 1 vertically equals 0. So I want it to be horizontal. I want it to be horizontal, so I say vert equals 0, and I'm getting these box plots. And then I'm getting this, the third one is that I'm saying x 2 and 0. So here I'm at row index 2, which is the third row, and column index 0, which is first column still. I want a scatter plot of exam 1 on the horizontal axis and exam 2 on the vertical axis. Yeah, that's what I am getting there. And then with that being said, I move to the second column. Second column, row index 0, which is the first row, I want it to be empty. I don't want to print anything there. So that's also always an option. You can have some of these plots empty. But on the right center, I want a box plot of final and vertical 0, so I want it horizontal. And then I want my third row, or row index 2 and column index 1, which is second column, to be a histogram of final, and I want orientation to be horizontal, so I want it to be horizontal, and I want to set the x label for second one is final. For the first one, I want my x label to be exam 1 and my y label to be exam 2 for left bottom. And then I just say plt.show. So just remember that there's nothing new here in this example. All I am saying is that you can mix and match between different types of plots. This is very good, and then you can add color and you can add different things to them. Okay, with that being said, let's focus on scatter plot with marginal distribution. That's Joint plots are used to explore the relationship between bivariate data as well as their distribution at the same time. This sort of task is much more fit for libraries such as Seaborn. It's not fit for Matplotlib, which has a built-in joint plots in Seaborn function. In Seaborn, we have a joint plot function. With Matplotlib, however, it's going to be harder. We'll construct a joint plot manually using grid spec with multiple axis objects instead. So grid spec is used for advanced customization of subplot grid on a figure. Let's see what's going on. So first of all, we have to import this new thing. So in practice, we don't use this that much, but still it's a very good idea to know about this. So from matplotlib.gridspec, import gridspec. Gridspec specifies the geometry of the grid that a subplot will be placed. The number of rows and columns of number of rows and number of columns of the grid need to be set. So we have to set that one. The power of grid spec comes in being able to create subplots that span rows and columns. Remember this. They can span rows and columns. Note the NumPy slice syntax for selecting the part of the grid spec each subplot will occupy. So you always start from top left, that's has index 0, 0. Then you move, when you move down, your first index increases, and when you move right, your second index increases. With that being said, I'm going to run this. It's going to be a little bit hard at the beginning to understand what's going on. And then we are going to focus on it a little bit more. So this is going to be example maybe 2, and this is going to be example 1. So here we have this, and you can see like it's a little bit like different than all of things that we had so far. But let's see what's going on. So I'm defining fig3 as plt.figure. So we have this constraint underscore layout, and that one you can either have constraints layout equals true, or rather than that you can have this plt.tight underscore layout. So either use constraint underscore layout equals true at the beginning, or plt.tight layout at the end. Yeah, either of them works. Okay, with that being said, let's see what's going on. So I define my fig3, then I define GS as fig3.add grid spec 3 and 3. And then I have axis 1. I say fig3.add underscore subplots gs0 and all. So I want my first one to be to include first row, so row index 0, which is first row, and all columns. So since I want all columns, I use this colon mark which shows all column. So because of that, we are getting this very on the top. You see the rectangle that includes the first row, but it carries all over the plot, so it includes all columns. And I give that the title gs0 comma color. Then I want f3 underscore x2 to be fig3 and subplots gs1. So I want my row index 1, which is second row, and then everything until last one, everything except last one. So it says second row all but last column. So this one includes this guy, gs1 comma colon -1. So it's second row and all columns except last column. Then I have this f3 underscore so I have this f3 underscore x4, and that's defined as, so this name is like somehow I'm selecting this name f3 underline x4. I could have mentioned this as any other names, but f3 underscore x4 is fig3 add subplot gs -1 and 0. So I want it to be last row. How do I know it's the last row? Because of this -1. So again, remember the NumPy slice syntax that we had in chapter 2. Comma 0. So last row, first column. This shows this one. And then I want it to have the title gs -1 and 0. And then I want f3 x5 to be last row 1 to the nth column. So I want it to be right here. Right here. And I want it to be last row and 1 to the nth column. So not the very last column, 1 to the nth column. And yeah, so f3 x3 also showed all rows from second row. So I don't want the first row, but all rows from second row. And so to the end and last column. So I want row 2 and row 3 as a matter of fact, and I want last column. So you can write it like this, or you could just say rather than one column, you could just manually mention all rows that you want. So all rows that you want is row index 1 and row index 2. So rather than this, I could just simply say this 1 and 2, and I mean you have to pass in a list. It's just easier to have it like this. It's just easier, but you could also mention the name of rows that you want. So with that being said, when you run this, you get this a little bit specific plot that we have. Now, with that being said, I want to get back to what we were talking about. Okay, and let me make sure that I've run everything correctly. Okay. Now if I run this, as you can see, I get this. So let me see what's going on. So I'm defining fig as always as plt.figure fig size 9 and 6. Then I define gs as grid spec of 4 and 4. So we have 4 rows, 4 columns, correct? Now I have one of them, which is main one, is this one, exam1 versus exam2, this scatter plot. That's the main one. In that one, I want rows index 1 and 2 and 3. So I don't want index I don't want index 0. I don't want the very top row, but I want rows index 1, index 2, and index 3. So remember this 1 to 4. It's the beginning is inclusive and the end is exclusive. And then I want columns 0, 2, 3. 0 inclusive, 3 exclusive. So it means that I don't want the last column. And on that one, so I define that as x underscore main, and then I define x underscore x as first row columns index 0 and 1 and 2, and then I want x underscore y to be subplot gs 1 to 4, so I want rows index 1 and 2 and 3, but column index 3, so last column. That's this guy. This is x underscore y. This is x underscore x, and this is x underscore main. So we have 3 objects. On x underscore main, I want scatter plot of exam 1 versus exam 2. On x underscore main, I want to set my x label as exam 1 and set my y label as exam 2. I want my x underscore x, which is this guy, to be a histogram of exam 1, and I want this one to be histogram of exam 2 with orientation equals horizontal. And then I just say this plt.title underscore layout, and if you run this, you get this result. Okay, next topic that we have is joint plots with box plots and histogram. Let me run this and then I talk about what it means. So here I'm doing almost the same thing, but a little bit different. On the top I have histogram, but on the right I have a box plot. So it's almost the same thing. Up to here is exactly the same thing. But I defined a dictionary called colors exactly as before. Then on main, I want to graph exam 1 versus exam 2, but I want my males to be in red color and my females to be in blue color. So for that, I say color equals df gender dot apply lambda x to colors, and takes care of different colors for different genders. And then I say x dot underscore main set x label exam 1, y label exam 2. Then I say x underscore x dot hist to be df exam 1. So I want my exam 1 to be a histogram here. And then I want my exam 2 to be a box plot right here. So x underscore y dot box plot is this. So again, remember these names x underscore y, x underscore x, and x underscore main. These are just arbitrary names. You could have named them anything else. And then I say plt.title underscore layout to make sure that these are very visible pictures. Okay, thank you. Next topic that we have is violin plots. Violin plots are used to visualize data distribution, combining the best of histograms and box plots. Conceptually, they are box plots, but they don't have a fixed shape. Instead, they have the kernel density estimation, KDE, which is similar to a histogram, to shape the body of the plot in such a way to give us a glimpse into frequency of elements in a distribution. So the best way that you can realize You can find out what I'm talking about is with an example. So here we are seeing the violin plot of exam 1, exam 2, and exam 3. And as you can see, it's a combination of a histogram and a box plot. And for example, we can have the scatter plots with violin plots. We can join them, and you can see like the minimum is given here for exam 1 and maximum given here. Exam 2 minimum is given here, and then maximum is given here. The median is given also, and then the bulk of distribution, as you can see, is right here or right here. Okay, next type of plots that we have is stack plots. Stack plots are used to plot linear data in a vertical order, stacking each linear plot on another. Typically, they're used to generate cumulative plots. So I'm defining x and then as 1, 2, 3, 4, 5, and then y is list of random integer random variables between 0 and 10, 0 inclusive, 10 exclusive, 5 of them, and then z, and then w. So if you can just see each of them. For example, y is going to be this, and then z is going to be this. Oops. So this is z, and then this is w. So with that being said, I can have the stack plot of these. Stack plot is going to be something like this. So the reason that we have this weird shape in the middle is that the third element of z and w, both of them are 0. It just randomly happened. So here, when you stack them, it's just x, it's just a y. Or you can do this. So we are defining a dictionary, and then we are running this. We need a legend. For the legend, we can have this. And as you know, you can have the legend outside or somewhere else. Yes. Okay. Next topic that we want to talk about is heat maps. Heat maps are color code variables based on the value of other variables. The color coding of variables is usually ascribed to an intensity variable, which changes the color of the cell it belongs to on a color spectrum. As the name implies, the color maps of heat maps are typically from cold colors like blue to warm colors like red. You can change this, however. You can change it, as we are going to see, giving us an intuitive feel of the intensity of a variable. So for that, let's just focus, for example, on DF correlation matrix. We have the correlation matrix here. So variables that we have is assignment, exam 1, exam 2, exam 3, final total. Of course, each variable has a perfect correlation with itself. So diagonally, all the numbers are 1. And assignments, as you can see, has 0.12 is the correlation with exam 1, 0.25 with exam 2, 0.22 with exam 2, 0.35. And by the way, these are real numbers, yes? So you can see that doing assignments will help students with the exams and with the final as well. And it has a very high correlation, 0.61 with the total. and exam 1 has some correlation with exam 2, with exam 3, and with final, and of course with total, and so on and so forth. Now, with that being said, we want to see, first of all, what is the DF core index? It's just the index is all of these assignments, exam 1, exam 2, exam 3, final, total. What are the columns that we have? Again, the same thing. It's going to be assignments, exam 1, 2, 3, final, and then total. So now we want to plot the heat map for this. How can we do that? With just these 3 lines, and we just graph a heat map. So fig size 9 and 6 does not work here again because output is in a square shape. Very similar to pie plot. We had the same thing for pie plot. If you make it 8 and 8, it's going to be bigger than 9 and 6. We also need names like X ticks and Y ticks. It's very ambiguous like this. So on the right side of, so I'm going to run the code and then explain what's going to happen. It's a little bit sophisticated, and we want to, however, if you do this, you get this very cool shape that like the blue is cold, red is hot, and it shows you what is going on. Before doing so, let's see what's going on. First of all, sometimes in text you can use this percentage sign and then F that we have. So like if you run this, 3 books cost equal percentage 0.3F. So this would be printed. 3 books cost equal 87.237. So the way it works is that here, rather than this, we are going to have this number 87 point, and then up to 3 decimals. You can have also this number 3 again as a percentage sign, and then pass in 3. So again, same thing will be printed. But what we have is that on the right side of percentage, we use a tuple. So here, on the right side of the percentage, we use a tuple to contain our values. Percentage D and percentage, for example, 3F are called as format specifiers. They begin with percentage sign followed by character that represent the data type. So data type can be, for example, percentage D format specifier is placeholder for integers. For that we use D, and similarly percentage point, let's say 3F is a placeholder for floating point number. So this is how you can replace a number in a text. With that being said, let me so we have this code, and maybe if I can break this down into 2 parts. So if I delete this part, then this would be printed. Okay, then here we are making it more complicated. We want correlations to be printed. So for that we need this knowledge. And it's just, if I do it like this, it's just easier to explain what's going on. So here, let's focus on this. Here we are adding x ticks and y ticks. So it's exactly like before, but rather than 9 and 6, I'm having 8 and 8. And then I'm adding this CMAP. So CMAP can be different arguments. The one that I personally like is cool warm. So cool is blue, warm is red. You can replace that cool warm with BUPU, and then you run this, you see what's going on. It's going to be like this. You can have Verdes, and if you have that one, it's going to be something like this. And or YLGNBU, you can have that one as well. You do that, you get this results. And PIYG, you can have that one as well for CMAP. And then it's going to be something like this. And there are also more options that you can just Google and find out them. But my personal favorite is just cool warm. So cool warm is my favorite. I have cool warm also here, and you run this, you get this. Okay, now how we are working on x ticks and y ticks. So for y ticks, I'm saying PLT y ticks range 0 to length of df core index, and then I want it to be df core index, and then I want them to have font size 12. So you can change font size to any number that you want, make them bigger or smaller. And x ticks, I want the columns to be printed. And then, so it's going to be range, our range is going to be from 0 to length of the F core columns. And we are not specifying step, so step is 1. And what we have as x ticks is df core column names, and font size is 12, and then rotation is 90. So here we are having them rotated. Yes, all of them are rotated 90 degrees. So with this we get this one. But in addition to this, wouldn't be that cool if we had like actual correlation numbers inside each box? That would be really good. For that we need this code. In this code, everything is the same, but now we have correlation numbers inside each box. Now, how did we do that? So the way that we did it is in these few lines. So I'm saying for y in range of df core shape 0. So this df core, first of all, let me show you what's happening here. This df core is this, and then we have df core shape. If you run this, you see shape is 6 and 6. And then, so this is you want that the first of these two numbers. So not necessarily always that we are plotting these heat maps, it's square, it can be rectangle as well. So this one gives us this first 6, and then this one gives us the second 6. Okay, now with that being said, so this df core dot shape 0 is just number 6. So for y in range 6, then for x in range 6, plt text x and y. So this x and y gives you the location of your text that you want to insert. Then you say percentage 0.1. So you're saying that you want only one decimal. You don't want more than one decimal. So that's the reason you are getting only one decimal. You could have gotten more than that. You could have gotten, for example, 2 decimals if you care about that. Yeah, you could easily have this 2 decimals. You run that, you get 2 decimals. But okay, let's leave it with 2 decimals. And then percentage. So rather than this number, rather than this quotation mark percentage sign 0.2f, what's going to be printed? The df car iloc x and y, which is the correlation that we are looking for. So that would be printed. And then we say horizontal alignment equals center, vertical alignment equals center as well, and font size equals 10. Again, you can change this. You can make it, for example, I don't know, 11. You do that, it's going to be a little bit bigger. You can see that it's a little bit bigger and more obvious. Make sure to play with this and understand this. Okay, that was about heat maps. The next topic that we have is Matplotlib 3D support. So Matplotlib has a 3D support. Several types of plots can be turned into their 3D variants. For 3D plotting, we don't use the regular axis object. We use the axis 3D object. What does that mean? Let's see. I'm going to run this, and then so as you can see, we have 3D plots here. So we have fig equals plt dot figure, fig size 8 and 6, nothing new there. Again, you can make this for example 8 and 8 to make it a little bit bigger. Yeah, so the difference is right here. This was 8 and 6, and this is 8 and 8. But we are saying x dot equals fig dot add plot projection equals 3D. So you can have projection of 3D or not. If you want 3D, you have to add this. And then x dot scatter df exam 1, df exam 2, df exam 3, and plt show. Now, that was one example. You can also mix and match between 3D plots and 2D plots. So this example, we are matching between these two. If you want a little bit bigger, maybe it's too big, maybe I make it, let's say 9 and 6. It's gonna be bigger, better, 9 and 6. Cool. Now, we have x dot x1 so x1 equals figure dot add subplot 2 and 3 and 1 projection equals 3D. So remember, we have 3 rows, 3 integers. First integer shows the number of rows, so we want 2 rows. Second integer shows the number of columns, so we want 3 columns. And third integer shows us the index. So index is 1, 2, 3. So first index moves toward the first row, which is row index 0, and then you move down, you move second row. So here we want only 3 of these plots to be 3D, index 1, index 3, and index 5. So index 1, 3, and 5, we want them to be 3D. Everything else we are cool. We don't want them to be 3D. With that being said, let's talk about 3D scatter plots and bubble plots. So for example, here I'm doing a scatter plot. So what's the difference here and before? I'm having X label, Y label on Z label. So we said x.set underscore X label, whatever you want your X label to be, and then x.set.Y label. And this one is new, x.set underscore Z label. We didn't have this before. And then here we are doing this again, scatter plots, but we have exam 1, exam 2, and exam 3. And then maybe I can also add this argument s, so I make it bubble plot. So let's say x is df exam, let's say df final, and let me run this. So as you can see, the first one is bubble plot, the second one is just simple scatter plot. So the only difference between bubble plot and scatter plot is that scatter plot has this s argument or size arguments. Okay, and then x2 is scatter of exam 1 and exam 2 and final exam. Okay, with that being said, we can also mix and match between graphs. So let's do that. So here we are doing exam 1, exam 2, and exam 3, and then we are doing also a heat map. So we are doing heat map as well. So the type of heat map that we have is blues. You can change that to whatever you want, but these are like very similar to before. Yeah, what we have here is exactly like before, and what we have here is exactly again as before. We're just combining scatter plot of exam 1, exam 2, and exam 3 with actual their heat map. Okay, 3D surface plots. Let me run this and then explain what's going on. So here we have a surface plot. In a surface, this results in a surface plot where the correlation values are between negative and 1, are the height of the surface plots. So we have these columns: assignments, exam 1, exam 2, exam 3, final, and total. Now here I want the height of this shape to be the correlation between each of these two. So the correlations are the heights. So here we say fig plt dot figure fig size 8 and 8. I'm defining these correlations as this dataset df.core and create new values for the x and y axis. Since column names strings won't work here, so I'm saying x equals y equals numbers between 0 and the length of correlation columns, and step is 1. X and y is then I'm defining x and y as the mesh grid of x and y, and then z I want to be correlations values. With that being said, I want x 3D. I'm calling this, rather than x, I'm just calling that x 3D. You can just call it x as well, it doesn't matter. So Fig add subplot 1 and 1 and 1. So the number of rows is 1, number of columns is 1, and index is 1. You can also do it in this way. So 1 comma 1 and 1 and comma 1. It's a little bit, I think, more easily to understand. So as before, this 1 and 1 and 1 means number of row, number of rows, number of rows, number of columns, and index. And then I say Ax 3D PLT surface, X and Y and Z, C map is cool bar. And then I have X ticks and I have Y ticks, and I have a font size of, for example, 8. I can have that as other numbers if I want, like maybe 10. So make them a little bit bigger. And if I run this, it's going to be a little bit bigger. This results in a surface plot where the correlation values are between -1 and 1, or the height of the surface plot vertices compared to XY plane. The last one that we have is counter plot. So if you are familiar with counter, we can have that as well. It's very similar to the surface plot, but rather than X dot rather than this plot underscore surface, we have X dot counter F, and with that you can have the counter plot of this. If you're familiar with counters, this can be very helpful. Okay, this was very important lesson in data visualization. Make sure that you know everything, you solve all the examples, and make sure you master this, because this was the core of data visualization. Thank you very much, everybody, for listening.